This is MIRI, the mid-infrared instrument on board the James Webb Space Telescope. Watch closely as light enters this incredible camera. A sophisticated network of mirrors and filters guides and splits the incoming light into various wavelengths, which are then resized and precisely directed onto ultra-sensitive sensors. Thanks to MIRI, Webb can observe extremely distant stars and galaxies objects completely invisible to the naked eye. But this feat is only possible because the camera is chilled down to a staggering 6 degrees above absolute zero. Why does it need to be so cold? In this video, we'll explore how Webb captures infrared light and reveal how something as simple as a sound wave cools its camera to mind-blowing temperatures. Plus, stay tuned till the end for a chance to win this awesome LEGO ISS model. How does James Webb's camera work? All of James Webb's cameras detect infrared light radiation invisible to humans. As light journeys through space, its wavelength stretches continuously. When objects are far enough away, their light becomes so stretched that by the time it reaches us, it's no longer visible. This puts a natural limit on how far we can see into the cosmos. MIRI sensors made from arsenic-doped silicon can detect these extremely stretched infrared wavelengths, pushing beyond that boundary. They work like ordinary camera sensors by converting photons into electrical signals. But to detect such faint infrared signals, MIRI sensors must be incredibly sensitive. Increasing sensitivity, however, comes with a downside noise. Whenever a camera points at something, its sensor picks up more than just the target light. Ambient light bounces everywhere, often too faint for our eyes to see, but enough to cause random noise in the image. If the target is bright, it stands out clearly against this noise. But when imaging something faint, like a distant galaxy's infrared light, the sensor's sensitivity must increase, and so does the noise. Because Webb detects infrared light, the problem intensifies. Every object in the universe emits heat energy, some as light. Most objects aren't hot enough to glow visibly, but emit abundant infrared radiation instead. The hotter the object, the more infrared it emits. This is the principle behind thermal imaging cameras. The challenge? James Webb itself emits infrared radiation, which could overwhelm its sensors. To prevent this, the telescope's cameras must be cooled to an astonishing -234 degrees Celsius, extremely cold. Just like Wondrium, today's video sponsor. Wondrium is an amazing learning platform offering courses across diverse subjects, including my personal favorites: technology, science, and space exploration. One standout course is the Search for Exoplanets, which dives into the technologies and methods used to discover planets beyond our solar system, similar to those on James Webb. Wondrium's vast library includes videos, tutorials, and documentaries, letting you learn directly from experts and their first-hand experiences. With fresh content every month, you'll never run out of fascinating topics. Enjoy ad-free learning anywhere, on any device, and as a special offer to the Primal Space community, Wondrium is giving you a free trial starting today. If you want to challenge yourself and expand your knowledge, Wondrium is the perfect place. Don't wait, click the link in the description below to start your free trial. Cooling James Webb's camera with sound. To achieve MIRI's operating temperature of -267 degrees Celsius, it's positioned behind Webb's massive 5-layer sun shield. This shield blocks much of the heat, cooling the cameras down to around -234 degrees. But MIRI, being far more sensitive than the other instruments, faces a bigger issue: dark current. This is when atoms inside the sensor vibrate and mistakenly register photons, adding noise. Since temperature measures how fast atoms vibrate, lowering the temperature reduces these vibrations, and thus dark current. Even at -234 degrees, atomic vibrations are still too high for MIRI's needs, so it's cooled even further to -267 degrees, just 6 degrees above absolute zero. At this temperature, atomic vibrations nearly cease, dramatically cutting noise and allowing faint infrared signals to shine through. How does NASA cool the sensor so drastically? It all starts at the bottom of the telescope with a device called a pulse tube. Inside the tube, 2 pistons move back and forth, compressing helium gas. To avoid vibrations that could disturb the telescope, these pistons move in perfect opposition, canceling each other's motion with precise timing. Moving rapidly like a speaker diaphragm, they create a low-frequency sound wave at 30 Hz. This wave travels down the tube, compresses at the end, creating a high-pressure zone, then rebounds, creating a low-pressure zone, and repeats. If new waves sync perfectly with returning ones, a standing wave forms with fixed areas of high and low pressure. By tripling this frequency, these waves combine to form a stationary wave with multiple alternating pressure zones. Since temperature and pressure are linked, these zones correspond to hot and cold areas. However, hot and cold areas alone don't change the overall temperature, they cancel each other out. To cool down, the hot areas must be extracted. 3 heat exchangers made from thin metal sheets are placed where hot and cold gases meet. These allow gas to pass while absorbing heat, creating a temperature gradient. Heat from the hot side is pulled away to radiators, while cold areas lose heat, dropping the temperature from room temperature to minus 256 degrees Celsius at the last heat exchanger. But how is this cold used to chill sensors at the opposite end of the telescope? Nearby is another set of pistons compressing helium in a separate tubing line. This line passes through the pulse tube's cold heat exchangers, chilling helium down to minus 256 degrees. Yet it's still not cold enough. The helium then travels up 10 meters of thin tubing to the cold head assembly, where it passes through a tiny hole less than 1 millimeter wide. Here, the helium undergoes the Joule-Thomson effect. It's compressed going in, then rapidly expands on the other side, dropping pressure and cooling drastically. This is why blowing air through pursed lips feels colder. On James Webb, this cools helium down to minus 267 degrees Celsius. From there, the helium flows over copper plates attached to MIRI's sensors, chilling them to their required ultra-low temperature. After cooling the sensors, the helium cycles back down and the process repeats continuously. When NASA designed James Webb, no cryocooler could reach this extreme cooling, so engineers pushed the boundaries of physics to create this marvel, all while fitting it into a compact space telescope. And now for something special, the winner of our last giveaway is Daniel Weinman. Congratulations! As always, we'll be giving away another amazing space-themed prize in the next video. To enter for a chance to win this fantastic LEGO space station model, sign up at the link below and leave a comment with your guess on how long you think James Webb will keep operating. Thank you so much for watching. I'll see you in the next video.